So far, we've been learning about the singly linked list. And in singly linked list, we can only move forward. But what if we want to be able to move forward and backward? Then we need a doubly linked list. In doubly linked list, we have 2 pointers. We'll have the next and the previous. But in singly linked list, we only have next. We don't have previous. So this way we can be able to move forward and backward. So let's go ahead and implement the doubly linked list. So we're going to start by creating our node class. So we have class node, and we have our constructor, and we'll have self, we have the data, and we'll have self.data is equal to data, and we have self.next is equal to none. And for doubly linked list, we have previous attributes. So we have self.previous is equal to none as well. Now let's go ahead and create our doubly linked list. So we have class doubly linked list. Here we have our constructor, and we have self like this, and we'll go ahead and have self dot head is equal to none. Now let's go ahead and implement methods that will allow us to move forward and backward. Then we can now go ahead and perform insertions, deletions, and other operations. And because we're working with doubly linked list, we can move forward, we can move backwards. So we're going to be having 2 methods for traversing our list. We'll have display for moving forward. We have display backward for moving backward. So for this, we have def display, and we have self here. To display forward, this is similar to the logic we use in singly linked list. What we need to do is just to move from one node to the other until we get to the end of the list. So we're going to be starting from the beginning. So we have current is equal to self dot head, and we have while current, then we print our data. So we have print, and we have current dot data, and I want to put an arrow after each data. So we have something like this to indicate an arrow, and we'll have the end argument so that the values are not printed in new lines. All of them should stay in one line. So we'll have just a space like this. We'll close our parenthesis. Then we have current is equal to current dot next. And this continues until we get to the end of the list. And in a situation whereby we're dealing with an empty list, we'll simply print none. So this is how we'll traverse forward. Now let's look at how we can traverse backward. And for this, we have def display backward. But before we can display backwardly, first we'll have to get to the tail of the list, and from there we'll start moving to the head. And before we do this, we need to confirm whether we're dealing with an empty list. So we have if not self dot head. If there is no head, then it means we cannot do anything. So we'll simply return. But if we're dealing with a non-empty list, the first thing we'll do is that we're going to traverse to the end of the list. So we're going to have current is equal to, that is, we're starting from the beginning, is equal to self.head. And we have while current dot next. Then we have current is equal to current dot next. But because we are using current.next, at the end of the loop, current should be the node pointing to none. So this time around, we're going to start moving backwards, and this is where we're going to use the previous attribute. So we have while current, and we're going to print the data. So we have print, and we have current dot data. We'll put an arrow, and we have our end argument. We'll close the parenthesis. Instead of using next, we're going to be using previous to take us backward. So we'll have current is equal to current dot previous. So this is going to take us backward all the way to the head of the linked list. So this is how we display backward. So now let's look at some of the operations we can perform on a doubly linked list. They are not too different from what we can do on a singly linked list. So let's start with insertion. And for insertion, we can perform insertion at different places. We can perform insertion at the beginning. We can perform insertion at the end. We can also perform insertion at a specific index or position. So let's start with insertion at the beginning. So we have insert at beginning, and we have the data that we want to insert at the beginning. We'll start by creating a new node. So we have new node is equal to node, then we pass in the data. Because we're inserting at the beginning, we need to make this new node the head of the linked list. But before we do this, we need to point the next attribute of the new node to point at the current head of the linked list. So we'll have new node dot next is equal to self dot head. Then before we make the new node the head, we need to confirm whether we're dealing with an empty list. If we're dealing with an empty list, we'll simply assign the new node to become the head. But if we're not dealing with an empty list, it means that we need to make the previous attribute of the current head to become the new node. So we have if self.head, which means we have a head already. We're going to have self.head.previous to be equal to the new node. Then afterwards, we're going to have self.head is equal to new node. So this is how we can insert at the beginning. So let's go ahead and try this out. And we're going to have DL is equal to doubly linked list. And we're going to insert at the beginning. So we have DL dot insert at beginning. We're going to pass in 100. We'll do again DL dot insert at beginning. Let's put 200 this time around, and let's display the element. So we have DL dot display. This is for forward display, and we'll run the program. So we'll have 200, 100, and none. So let's put another element. So we'll call this one 300, and we'll run it. All working well. So let's display backward. So we have DL dot display backward. Then run it. You can see it has been displayed backwardly. So this is how we insert at the beginning of a linked list. Now let's see how we can insert at the end of a doubly linked list. So we have def insert at end. We have our data, But before we go ahead and perform the insertion, we need to confirm that we're not dealing with an empty list. And if we're dealing with an empty list, all we have to do is make the node to become the head. So we have new node is equal to node. We'll put in the data. And if not self.head, if the list is empty, we'll simply have self.head is equal to new node and return. But if it is not an empty list, we'll traverse to the end. So we have current is equal to self.head. We'll start from the beginning, and we'll have while current dot next, and we have current is equal to current dot next. So this is going to take us to the very end. And when we get to the end, we're going to have current dot next is equal to new node. Then we'll have new node dot previous is equal to current. So this way we can be able to insert at the end. So let's try it out, and we're going to remove this, and I'm going to be inserting at the end. But first of all, let's run it and see what we have. So currently we have 100 at the end. So we have dl.insert at end. So let's have 400 there and run it. So we successfully inserted at the end. So let's try another example. We have dl.insert at end, and we put 500, and 500 was inserted at the end. So this is how we insert at the end. So now we're going to be inserting at a given position, and for this we have insert at position. We have our data and we have the position where we want to do the insertion. But before we go ahead with the insertion, we need to confirm whether we are inserting at the beginning. Since we already have a logic for inserting at the beginning, we'll simply make use of it. So to check whether the insertion is at the beginning, it means the index has to be 0, or the position has to be 0. So we'll have if position is equal to 0, then we'll have self.insert at beginning, then we'll pass in the data. So this is going to handle a situation whereby you are inserting at the beginning. But if we're not inserting at the beginning, then we'll need to create a node. So we'll have new node is equal to node, then we pass in the data. Then we're going to start from the beginning. We'll have current is equal to self.head, and we're going to be using count as a pointer to keep track of our traversal. We'll assign it 0. Now we're going to perform a traversal, and we'll have while current and count less than position minus 1. We want to get to the position before the actual position where we want to do insertion. So we want to get to a position before where we want to perform the insertion. So for this, we're going to have current is equal to current dot next, and we're going to increment our count plus equal to 1. So this is going to take us to the node just before where we want to perform an insertion. And to be sure current is pointing to a node and not none, we can have if not current. If it is not current, it means that we're not dealing with a node. We're going to raise an index error. So we'll have raise index error. And for the message, we'll write position out of bounds. Then, since we're dealing with an actual node, we can now go ahead and perform our insertion. So we'll have new node dot next is equal to current dot next, and we have new node dot previous is equal to the current node. Then the next thing to do is we need to confirm whether the present current node is pointing to a node or pointing to none. If it is pointing to a node, it means we need to make the previous attributes of that node to point to the new node. So we're going to have if current dot next, then we have current dot next dot previous is equal to the new node. Then we'll now go ahead and assign the current dot next to be equal to new node. So this is how we can insert at a given position. So let's try this out, and we're going to have dl dot insert at position, and we're going to be using 111 for the data, and for the position we'll put 2, and we'll run it. You can see it is successful. It inserted it at the position 2, 0, 1, 2. So let's try it out at position 4. So I'm going to copy this and paste it below, and this is going to be position 4. So let me use 1000 and run it. So this is successful. So let's try it out at a non-existing position. So let's make this 8 and run it. So you can see we'll have an index error, position out of bounds. But if I change this to 0, this is going to use the logic for insertion at the beginning. And you can see 1000 is inserted at the beginning. But if you look at this output, you can see that we have 1000 at the beginning, which is wrong. So let's look at our code. And the reason for this is because we performed insertion at the beginning with this, and this also performed insertion at the beginning as well. So we need to put a return keyword here. So simply have return. So let's run the program again, and this time around it is working well. So this is how we can insert at a given position. Before we get to deletions, let's see how we can get the value in a given position in a linked list. So here we're going to have def get value, and we're going to be providing the position where we want to get the value. But before we go ahead and start searching for that value, we need to confirm whether the position provided is indeed a valid position. So we have if position is less than 0. This is an invalid index, so we'll raise an exception. So we'll have raise index error. And for this, we can have invalid position as our message. Then if the position is actually a valid position, then we're going to traverse to that position and get the value. So we'll start from the head. We'll have current is equal to self.head. And we're going to be using the count pointer to keep track of our movement. So we'll have count is equal to 0. So we'll have while current. And if count is equal to position, it means that we've gotten to the position where we want to get the value. So have if count is equal to position, then we'll return current dot data. Then if not, then we'll go to the next node. So have current is equal to current dot next, and we increment the count. So count plus equal to 1. And if at the end of the loop we don't get to that position, it means that the position provided is not a valid position. So raise an index error. So have raise index error. And for this, we're going to have position out of bounds. And we'll go ahead and try this out. So we'll have result is equal to dl.getValue. We'll provide the position to, and we'll print the result. So let's go ahead and run it. So have 200 at position 2. So let's try position 5. Position 5 is 400. So let's try a non-existing position, maybe 9. You can see we have index error. Let's try an invalid index. So can put -1 here. We'll still have index error. So this is how we can get the value in a given position in a linked list. So let's go ahead and see how we can perform deletions. And just like insertion, you can delete at different places. You can delete at the beginning, you can delete at the end, or you can even delete at a specified position. So we have deletion, and we're going to be starting with deletion at the beginning. So we'll have delete at beginning. To delete at the beginning, all we need to do is to make the next node after the head to become the head of the linked list. But before we go ahead and do this, we need to confirm that it is not an empty list. So we have if not self.head. Then we're going to raise an exception. So we have raise index error. And for the message, we can have empty list. But if we're dealing with a non-empty list, we can simply make the next node after the head to become the head. And to do this, we're going to have self.head is equal to self.head.next. Now we're going to assign the previous attribute of the head to none. So we have if self.head, and we'll have self.head.previous is equal to none. So this is how we can delete at the beginning. So let's go ahead and try this out. We're going to delete at the beginning. So we'll have dl.delete at beginning, and we'll run the program. You can see that we successfully removed the node at the beginning. We can try it again. Currently 300 is at the beginning, so we'll have dl.delete at beginning, and this is going to achieve the same thing we deleted at the beginning. So this is how we delete at the beginning. Now let's look at how we can delete at the end. And here we have delete at end. And first of all, we have to confirm that we are not dealing with an empty list. So we have if not self.head, then we'll raise index error. So this is empty list. We'll close the parentheses. Then the next thing we'll do is we'll check whether we're dealing with a single item linked list. So we have if not self.head.next. If this is a single item list because it doesn't have a next node, then we're going to have self.head is equal to none. We'll simply remove the head and we'll return. But if we're not dealing with an empty list, we're not dealing with a single item list, then we're going to traverse to the end. So have current is equal to self.head. Then we're going to move to the very end of the list. So have while current dot next, and we're going to have current is equal to current dot next. This is going to take us to the very end of the linked list. And when we get there, we're going to break the link between that last node and the other nodes. So we're going to target the node before the last node and assign the next attribute to none. So we have current dot previous dot next is equal to none. And this way we can be able to delete the last node. So let's go ahead and try this out. I'm going to remove this and let's run the program. And currently we have 500 at the end. So have dl.delete at end. Then we'll run it. So remove the 500. If we want to remove 400, I'm going to paste this here, and this is going to remove the 400. So this is how we delete at the end. Now let's look at how we can delete at a specific position. So we're going to start by having delete at position. And for this, we're going to have the position where we want to delete. But before we delete, we'll confirm whether we're dealing with an empty list. So we have if not self.head, then we'll raise an index error. So we'll have raise index error. For the message, we're going to have empty list. Then the next thing we're going to do is to confirm whether the index or the position is a valid one. So we'll have if position is less than 0, which means it's an invalid index, we're going to have raise index error. And for the message, we can have invalid position. Then another thing we can do to save us time is to check whether the position is 0. If the position is 0, it means we're deleting at the beginning. We'll simply use our method for deleting at the beginning to handle that. So we'll have if position is equal to 0. So we'll have self.delete at beginning, and we'll return. This is going to perform a deletion if the index is 0 or the position is 0. Now, in a situation whereby we're not deleting at the beginning, we'll have a valid index, we're not dealing with an empty list, what we're going to do is we're going to traverse to that position. So we'll start from the head. So we'll have current is equal to self.head. And we're going to be using counts for our pointer to keep track of our movement. So we'll have count is equal to 0. Now we're going to traverse or move to that position. So we'll have while current and count is less than position. We have current is equal to current dot next, and we have count plus equal to 1. So this is going to take us to that position where we want to perform deletion. But before we go ahead and perform the actual deletion, we need to confirm that we're dealing with an actual node. So we have if not current, which means it is a none. So we'll simply raise an index error. So we'll have raise index error. And for the message, we're going to write position out of bounds. We'll close the parenthesis. In a situation whereby we're dealing with a node, what we're going to do is to get the node before the position where we want to perform deletion. So we'll have if current dot previous. When we get to that node, we're going to make the next attribute of that node to point to the node after the node in the position where we want to perform deletion. So we'll have current dot previous dot next is equal to current dot next. So we've broken the link between the previous node and the current node. So the previous node is now pointing at the node after the current node. So let's take care of the node which the present node is currently pointing at. So have if current dot next, and here we're going to have current dot next dot previous is equal to current dot previous. And with this, we have completed the method for deleting at a given position. So let's try it out. I'm going to remove this and run it. So let's see whether we can delete at position 1. So we have dl.delete at position, and we're going to put 1 as our position, and currently we have 1 at that position. So let's see whether it will be removed. So we'll run it. 300 has been removed. So let's see if we can delete at position 0, and this is successful as well. Let's try to put a non-existing index, maybe 10, and we'll run it. We'll have an index error, which is position out of bounds. If we try to delete with an invalid index, let's say -1, we'll still have a trace back. So this is how we can delete at a specific position. Before we conclude the doubly linked list, let's see how we can get the length of the list. So we have def length. So have self here, and we're gonna be starting from the beginning. So we'll have current is equal to self dot head, and we're gonna be using count to keep track of our movement. We'll assign it to 0, and we'll have while current, and here we're going to increment the count. So we have count plus equal to 1, and we have current is equal to current dot next. Then we'll return the count. So we'll have return count. So let's try it out, and I'm going to remove this. Currently we have 1, 2, 3, 4, 5, 6 and 7 items here. So I'm going to have result is equal to dl dot length. I'll print result and run it. So I have 7 items, so the length is 7. So this is how you can determine the length of the list. Next, we're going to be implementing a method for searching for a given value in a linked list. So we'll have def search, and we'll have self, and then we have the value which we are searching. So first, we're going to start from the beginning. So we'll have current is equal to self dot head. Next, we have count, and we'll assign it 0. With this count, we'll keep track of our movement or the index or position. So when we finally get the value, we'll simply return the count, which is equivalent to the index of that value. So we'll have while current. Now we want to compare the value of the current node with the value we're looking for. So we have if current dot data is equal to value, then we'll return count. Then we'll continue. We'll have current is equal to current dot next. Then we increment the count. So we have count plus equal to 1. But in a situation whereby we don't get the value, we'll simply return -1. So we'll have return -1. So let's go ahead and try this out. And currently we have these values in our linked list. So let's see if we can search for 200. So we have result is equal to dl.search, and we'll provide 200 and print the result. So we'll have print result, and you can see the index is 2, which is correct. So this is how we can search for a given value in our linked list. So with this, we have completed our doubly linked list.